Hello everyone. I'm Mohamed Movahedi. I'm a simulation and computational method RSR for NHERI GSC. Today we will have Dr. SoungEil Houng. He's a PhD student, from University of California, Berkeley. Uh, if I want to give you a short bio about him. He's a PhD candidate in the civil and environmental engineering department at UC Berkeley. His prior professional experience is in seismic hazard analysis for nuclear power plant sites in South Korea. He holds master's degree in both seismology and civil engineering, as well as a bachelor degree in Earth system sciences. His research interest includes seismic hazard and risk analysis, with a particular focus on developing scalable computational frameworks to reduce complexity in large-scale assessment. Uh, uh, Sungil actually is from another lab. If you want to know about his lab, it's the disaster risk analysis lab at UC Berkeley. This lab is led by Professor Luis Ceferino. Develops they This lab develops probabilistic models and decision tools to improve the resilience of infrastructure systems under extreme events. The group's research combines risk analysis, structural and network modeling, artificial intelligence, and uncertainty quantification with applications to earthquake, hurricanes, and cascading infrastructure disruptions. Without further ado, Sung, if you want to start the presentation, I can hand it over to you.
Good morning, everyone. Can you see the screen and can you hear my voice as well? Okay, thank you. Thank you very much. I'm happy to have a chance to give a talk in NHERI GSR presentation. And my presentation title is A Scalable Scenario-Based Earthquake Risk Modeling via Linearized Ground-Motion Fragility Coupling and Probabilistic PCA. And let me start the presentation. This is an overview of my presentation. I'd like to first introduce the traditional way to perform the regional risk analysis, and I explain why it is computationally expensive. And I'd like to introduce our proposed framework in two different steps, and then we will verify our method using three different numerical examples. So this is a traditional way to conduct the regional scale seismic risk analysis. So for single building case, we have a well-established method called PBEE, or the Performance-Based Earthquake Engineering Framework. So in PBEE framework, we sequentially calculate the intermediate quantities that relates the input hazard to the final consequential loss. So given the ground motion, by performing the structural analysis, we calculate the engineering demanding parameter, such as like an interstory drift. And given this parameter, we calculate the damage of the building. And given the damage, we calculate the consequences, for example, the number of faculties or number of casualties or the financial losses. And we can extend this to the regional analysis as well. So, but what makes the regional scale special than the single building case is that high dimensionality of the problem. So, okay. So first we need to define the map of assets given the rupture scenario first. And then given the ground motion model, we generate the map of ground shaking. And given the map of ground shaking, we calculate the damage map of the buildings and then get the loss of the map, a map of the loss. So if you are interested in n number of buildings, then we need to calculate n ground motion intensities, n damages, and n losses. And for the metropolitan area building portfolio, this number grows very fast. So for whole Bay Area, the number is 1.3 million. This is a significantly high dimensional problem. And this is the problem statement of the regional scale regional risk analysis. So given this high dimensionality nature of the problem, uh, the primary challenge comes from the ground motion simulation. So typically for ground motion simulation, we incorporate two different models. The first model is ground motion model to calculate each site's mean and variance of the ground motion. And we also incorporate the inter-site correlation of the ground motions, the correlation model, the spatial correlation model. So this process incorporates the generation of n-dimensional Gaussian random variables. And to generate these random variables, the computation time scales with n to the cube to generate um, the matrix operator to realize the covariance of the variables. And also simulation requires the O n to the square computational complexity. And damage modeling is less computationally expensive than ground motion simulation case because the simulation time complexity scales linearly with n. So my point is that most of the computational burden is from the ground motion simulation side. So to reduce the number of sites where the ground motion intensity will be calculated is very important because n to the cube is a huge growth rate of the computational time. So researchers typically does is to adopt the ground motion grids. So if the asset is located in the same grid, then the same ground motion intensity is applied. And this reduces n. In this example, we have 10 buildings here. So we should generate 10 different ground motion intensity, but this 10 number of 10 becomes 4. So computational burden reduces a lot. However, this also introduces the bias in the final loss because the assets in the same grid actually does not have the same ground motion intensity in reality. And this exemplifies that case. The figure on the left shows the different ground motion grading strategies from fine to coarse ones. So in each map, the red dot indicates the points where the ground motion will be generated. And the figure on the right shows how the grid design influences the final loss. So as the resolution of the grid becomes coarser, we intuitively can be predicted. So the error becomes larger and larger. So here's my research question. So can we effectively simulate the ground motion and resulting damage without ground motion grading assumption? And also make this computationally feasible. So from here, I'd like to introduce our proposed framework. So the first one is linearization of the ground motion and damage coupling. And second one is dimensionality reduction using probabilistic PCA, which is related to the computational burden to reduce the computational burden. So first, there is the linearization part. So I want to introduce first how traditionally the damage simulation is done in regional scale. These are composed of two different steps. The first one is ground motion simulation. So given the rupture and the site, we incorporate two different standard normal random variable to get the ground motions. And these two random variables are multiplied to the standard deviation of the ground motion that is from ground motion model, empirical ground motion model. And by adding the mean ground motion intensity from the model as well, we can get the logarithm of ground motion intensity at the site. And given this ground motion intensity, we usually um, use the probability of failure to get the damage state of the building. So this probability of failure is modeled as log normal CDF in typical. So what we do here is that in simulation, we draw the sample randomly from 0 to 1. And if the sample is greater than probability of failure given the ground motion intensity, we model them as safe. If not, we model them as fail. Or in other words, we calculate the difference between this random sample and the probability of failure. If that number is negative, then we model as fail. If that is positive, then we model that as a safe state. Um, So what I did here is to slightly modify the uniform sample U with the different formulation. Rather than directly draw the sample from 0 to 1, we can do the same thing by first sample the standard normal random variable Z and project that into the Gaussian CDF, then we can equally get the uniform sample. And the thing here is that log normal CDF is commonly appeared in both terms, and the log normal CDF, no, the CDF of a Gaussian distribution is a monotonically increasing function. The removal of this phi does not affect the sign of the function g. And this sign of function g is the only parameter we care, only thing we can care. We doesn't care of the value. So if the sign is preserved, then the final damage state that doesn't change. So if we remove this phi from the equation, we can create a new damage state, limit state function, small g, as the equation 2. We also can use this g to determine the damage state of the building as well. So combine these equations together, the the limit state function g can be represented as a linear combination of three different standard normal variables, two from the ground motion model and one from the fragility curve. And because the linear combination of standard normal variables are normal as well, following some normal distribution. So we can simplify this two-step procedure with one-dimensional Gaussian random process, and those parameters are from either ground motion model or the parameters of the fragility curve. So we can model the ground motion and damage simulation coupling with the Gaussian random variable. If we have a single building, this becomes one-dimensional Gaussian. And beta and theta parameter from fragility curve. And mu and standard deviation models are from ground motion model. We can extend this to n-dimensional case. So if we have n sites and the model parameter becomes, the output becomes the n-dimensional Gaussian random variable. And this figure shows how this linearization is achieved. So this figure shows a traditional fragility curve space, how the function g the sign of function g changes. And if we linearize this, then the limit state becomes linear, and the direction where this g value changes is unique. So we can model the sign of g in this direction, which has a slope of beta over 1. And if we extend this ln y as a linear combination of two random variables that is appearing in the ground motion modeling, then the limit state is still exhibiting the curvature, but in the linearized space, it is perfectly planar plane. And if we are considering a multiple limit states, 1 to 4, for example, the no damage and slight damage, moderate damage, extension damage, and complete damage, then this, in the linearized formulation, this boundary becomes parallel, and also they are linearized. And the direction where the sign of G changes is the normal vector of these planar planes. So we just model the G value along this normal vector. So as I mentioned, for the multiple building, this one-dimensional Gaussian becomes n-dimensional Gaussian, but the number of dimension is still high. So we need to reduce the dimensionality of this problem as well. And what we can do is that if the variables are highly correlated, the dimensionality can be reduced easily. This shows how it works. So we can simulate the damage of the building G function using the Gaussian random variable. So this is the G of site 1, and this is the function G of site 2. If they are highly correlated, it is redundant to produce the, sorry, it is redundant to simulate the variance of the data in two directions. It would be sufficient to model it in lambda 1 direction, which shows the largest variance. But if their correlation is still exists, but the variance cannot be explained by the first component, the first component that exhibits the largest component, then the second component should still be used for the full simulation of this data, so that in this case, the dimensionality reduction is not effective. So this is a typical principal component analysis. So if the variables are highly correlated, then we can reduce the dimensionality in this case from 2 to 1. But in this case, if they shows lower correlation, the dimensionality cannot be reduced. However, we found that in the linearized formulation, the variables are not highly correlated. They rather showed the modest correlations rather than high correlation. So these correlations cannot be ignored in the simulation. And also, due to this lower correlation coefficient, the standard PCA does not work because thus the because they cannot be ignored. So we need some specialized technique to address this problem, and we applied the probabilistic PCA. So in traditional principal component analysis, they find the orthogonal directions that maximizes the variance of the data, the direction 1 and direction 2. So if the magnitude of axis of first component is the second component is negligible to the first component, then we can just ignore the second component. But if the second component is still non-negligible, we can decompose this data into the highly correlated part and independent part. So how it does is that if we can decompose the data into highly correlated one and independent one, we can apply the standard PCA to this highly correlated data. So in this case, because the magnitude of second principal component is negligible to the first component, we can reduce the dimensionality here. And this is also exhibiting a high dimensionality, but this is independent noise, so the computational burden is not so high in this case. So to conclude that to simulate G, we need a matrix operator L to generate the n-dimensional Gaussian random variable, which is n by n matrix. And this should be multiplied with the n-length vector. So computational complexity of this operator is n squared. But if we can ignore some the most of the principal components, trailing principal components, then the matrix operator becomes, the size of the matrix operator becomes n by t, which is less than n. And then the computational complexity is t times n. And if t is much, much less than n, then it becomes effectively O of linear with n. And this, if we express this as a matrix form, it looks like this. So before applying the principal, probabilistic PCA, the variance of the Gaussian random variable component should be done by multiplying n by n matrix with n length factor. But after applying the probabilistic PCA, this process becomes n times t matrix times t length factor plus the independent noise part, which is computationally cheaper. So from here, I'd like to introduce our proposed framework for ground motion damage modeling and which is divided into three parts. First one is verification of our method, and second part is dimensionality reduction with the scenarios with different spatial extent of buildings, and third one is the comparison of computation time. And this is a slide for the experiment done with the 10,000 buildings in San Francisco downtown. And I compared the damage modeling result using our framework with the one from the SimCenter R2D software, which uses the traditional framework. And for the proposed framework, we use the t equals 1. That means we reduce the dimensionality of the problem from 1,000 to 1. And this figure shows each building's the most frequent damage state across 10,000 Monte Carlo simulations. And we found that among 10,000 buildings, around 950 matches exactly, and 48 exhibits the one damage state level differences. And for the building X, which exhibited the one level damage state difference, I plotted the distribution of the building damages across 10,000 Monte Carlo simulation. But they looks very similar, even though the model damage state is different. So that means our framework is working well with this fits well with this benchmark curve, benchmark damage state outputs. And in this example, we apply the method with two cases exhibiting different spatial extent of the buildings. They are composed of around 15,000 buildings. And the first one is San Francisco downtown, and the second one is the San Francisco Bay Area. We try to fit the loss curve calculated using traditional framework with one by our proposed framework. And what we found was that t equals 1, that means dimensionality reduction from 15,000 to 1 is sufficient to simulate the loss curve close to the traditional one in San Francisco downtown case. But for the same t equals 1 Bay Area case, they exhibit some deviation from the traditional one. So In this case, we required the required number of t is 20, but still it's a huge reduction of dimensionality because originally it was 15,000. And we can see that the error is becoming close to zero as we increase t, but t equals 20 still exhibits only the around 2.5% error. So this example shows that we need a large number of t's for the largest spatial extent of asset if someone uses our framework. And then this shows the numerical example for comparison of the computational time. So we compare the time difference between the traditional and the proposed method using the building portfolio of San Francisco Peninsula, composed of 30,000 buildings. And the computation time growth rate for the traditional method, the red one, is O of n squared as predicted by theory. And for our framework, the computational complexity is scaling with n. And for 30,000 buildings, it was 110 times faster than traditional method. And theoretically, for 1 million buildings, it should be 3,500 times faster than the traditional method. And this is summary. So we first linearized the coupling of ground motion and density modeling by the change of the variable. And with that linearized formulation, we reduced the dimensionality using probabilistic PCA. And by applying this probabilistic PCA, we were able to achieve a efficient simulation of regional scale density modeling, and this also showed the high accuracy against the benchmark curve. That's pretty much I prepared, and thank you very much.
Thank you so much. So if anyone has a question, it's now time to ask those questions.
So I have a quick question. I'm not in this related field, but I just want to ask, what is the reason of using Monte Carlo simulation?
The reason of using Monte Carlo simulation is that we don't have a closed form solution for the risk analysis. So given the asset, and if we are able to solve mathematically what is the consequence, then we don't need the Monte Carlo simulation, but there is no closed form solution. So we have to rely on the Monte Carlo simulation to calculate the annual loss or something that is related to the probabilistic scheme.
Thank you. Thank you so much.
Any other questions? So, SoungEil, I have a question. Have you ever tried this thing to like simulate to examine the effect of such a thing on other infrastructures, like I don't know, electric grid, road blockage, road transportation systems in the area, how they can actually like affect other infrastructures within the same physical environment?
I haven't applied this to the other system than building portfolio. The reason I chose building portfolios to show is that because they are dense and the number n grows very fast. So I think this is the most worst case in ground motion simulation case. So, but Yeah, sure. I can apply this to the other consequences like the power outages or road network. So yeah, this could be the exciting field that I can investigate further. Yeah, sure.
Okay. Uh, uh, Thank you, SoungEil, for the great presentation. Uh, uh, you can see his email here. Again, I'm Mohamed Movahedi. I'm the RSR for this subcommittee. If you want to present your research, if you see your group doing a very exciting research that you think it's very interesting to other people, uh, uh, you're more than welcome to email me. I can schedule a meeting and or uh, like a meeting also. Okay. Just
Thank you
looking.
so much, Mohammed, for invitation.
Of course, of course. Uh, okay, Robin, is that it? Do you have
That's
anything
it.
to add?
Thank you. Yeah,
Okay.
nope, you're it. Thank you so
Yeah.
much for all of your hard work, Mohammed. And then SoungEil, thank you so much for your presentation today. And the same thing with Najib and Clara, who are in the other room. Thank y'all so much for all of your time and sharing your research with everyone.
Thank you, everyone. I just wanted to add this simulation and computational method is not limited to structure or any kind of other disciplines. If you are working in other fields, if you are working in a multidisciplinary social science, like whatever that uses a simulation or computational method, you can actually reach out to me to schedule something like a presentation. It's a very good idea to present your idea, like your research to other people. They can give you feedbacks. It can shape collaborations and further. You can get recognized for your research. Actually, okay.
Thank y'all so much. I hope everyone has
Thank
a
you.
wonderful weekend.
Thank you, everyone.